Okay, so now let's move back to our first neural network, the one where we try to predict the labels on handwritten numbers. Yeah, so we have these images of handwritten numbers 0 to 9, and we want to predict, given that image, whether the number is indeed 0, 1, 2, 3, all the way up to 9. So let's start by loading our data. So I'm going to have train images and train labels. And we're also going to load the test images and the test labels. And we're going to load this from datasets, mnist, load data. Okay, so let's run this. Apparently no typos, so just to remind you, let's oops, I won't have the images. Now look at the shape. So basically what we have is 60,000 train images, and each image is a 28 by 28 matrix. So these are the pixels. So in the notebook we actually plot them, so you can look at it there. I'm not going to repeat that. The thing that's important is that if you look at the train images, so let's look at the first one. And the thing that we're interested in is what's the minimum value in that matrix. And that minimum value is 0. And if you look at the max value in this matrix, the max value is 255. Now, one of the things when you do neural networks is that given the optimizers that we use, it's actually useful to normalize your input values and make sure that they're between 0 and 1. Yeah, so we're going to do that. So we're going to have train images. It's going to be equal to the train images that we just loaded, so the original ones, and I'm going to divide it by 255.0, and we're going to do the same with the test images. So test images equals test images divided by 255. Yes, I'm going to run this. So now when we look at the max value of train images, it's 1. Yeah, so now I've normalized the inputs, and they're going to be between 0 and 1, so that usually helps to get the optimizers working, so they're going to be faster and give us the results sooner. Another thing that we do in the notebook is that we actually plot 25 of these images together with the correct labels, so you can look at that, look at the code, see how it's done. I'm not going to repeat that here. Here we're going to move straight into the definition of the model. So we're going to define our model, and we're going to be using keras, and we're going to define our layers sequentially. So we use keras dot layers, and the first statement is flattened. So this is actually not a layer, but what it does is it looks at the input shape, and in our case the input shape is 28 by 28. And instead of working with matrix, we're going to flatten the matrix. So we're going to glue each row to the previous one, such that the matrix becomes basically a very long vector. Yeah, so it's going to be a vector with size 28 times 28 and then 1. So the shape is going to be 28 by 28 and then 1. Yeah, so sometimes that's useful too, that's easier to work with. It depends also a bit on the solver that you're using. Some solvers can actually work directly with the matrix, others can't, so then you have to flatten the matrix into a vector. So these are our inputs. So 28, 28. Then we're going to define our first layer. It's going to be a dense layer, which means that each node in this layer and the previous one, which are the inputs, are going to be connected. And we're going to specify the 128 nodes. And the activation that we're going to be using is ReLU, which means that if the output from the previous layer is negative, then ReLU will give us a 0, so it's not activated. And if it's positive, it actually gives this positive value. Yeah, so I'll come back to that in a second. Then we go to our final layer, which is also going to be dense. So again, we use all the connections between this layer and the previous one. But now I'm going to have 10 nodes, meaning one node for each possible label. Yeah, so the labels are 0, 1, 2, 3, up till 9. So these are 10 different labels. And the activation now is going to be different. It's going to be softmax. Yeah, so we've seen the softmax function before. Basically what it does is it gives us a probability distribution over these 10 labels. So basically the final layer tells us what is the probability that the image that we put in is a 0, the probability that it's a 1, and the probability all the way up to that it's a 9. And then of course when we have to predict, we're going to choose that label that actually has the highest probability. Yeah, so that's the most likely outcome of our model for that particular image. So then we need to compile the model. So we specify an optimizer. And a safe choice is usually Adam. We're going to specify our loss. And that's going to be sparse categorical cross entropy. And finally, we can specify the metrics that we want to see when it's actually fitting the model. And here we specify only one, but this is a list, so you can specify more. And we say that we want to keep track of accuracy. Yeah, so let's see whether we didn't make any mistakes. Yep, I did make a mistake. So what do I do wrong? Optimize with Adam, metrics accuracy. What is it complaining about? Ah, sparse. That's indeed a typo. This shouldn't have been a period. Okay, now it gets it. So we can continue. So basically what happens is that the output of a layer is the weights that we want to determine. So let's say that's a matrix W times the input, which comes from the previous layer. So when we start with the first layer, these are simply the outcomes between 0 and 1 from the images that we have. And then plus a constant, or it's sometimes called a bias. And then basically what ReLU does is it says, take the output, and then the outcome for the next layer is either the output level or 0. Yeah, so when output is negative, the max of output and 0 is 0, so the node is not activated. And when it's positive, the outcome is basically output itself. So then the final step, which is going to take a bit of time, so I'm going to stop the video, but we use model fit, and we specify the images. So these are the inputs. Then the thing that needs to be fitted are the labels. So we want to get the correct prediction on the labels. And we can specify the number of epochs, which is the number of times that it actually uses the data that we have, the number of times that each observation that we have is used in the fitting. The choice of epochs is something we'll come back to later on. It's basically the trade-off between under and overfitting. So now we run this, and as you can see it starts to fit, and it goes first epoch 1, then 2, etc. all the way up till 10.